Hey everyone! Today we're tackling a Leetcode problem called count subarrays, where max element appears at least k times. It sounds a little tricky, but don't worry, we'll break it down step by step and find an efficient way to solve it. Ready? Let's dive in. Alright, so the problem gives us a list of numbers, called nums, and a positive whole number, k. Our goal is to count how many subarrays, continuous slices of the original list, have a specific property. That property is, the single biggest number from the entire original list must show up in that subarray at least k times. We just need to return the total count of such subarrays. The constraints tell us the list can be pretty long, up to 100,000 elements, and the numbers themselves can be quite large, but k is also reasonably sized. Let's look at the first example. The list is 1, 3, 2, 3, 3, and k is 2. First, what's the biggest number in the whole list? It's 3. Okay. So we need to find subarrays where the number 3 appears at least 2 times. Let's list them out. We have 1, 3, 2, 3. That works. Then 1, 3, 2, 3, 3. That has 3 3s, which is definitely at least 2. Then 3, 2, 3, 3, 2, 3, 3, 2, 3, 3, and finally 3, 3. If you count those up, yep, there are 6 of them. So the output is 6. Now for the second example. The list is 1, 4, 2, 1, and k is 3. The maximum number in the whole list is 4. We need subarrays where 4 appears at least 3 times. But wait, looking at the list, the number 4 only shows up once in total. So it's impossible to find a subarray where it appears 3 times. Therefore, the answer is 0. Okay, what's the first, maybe most obvious way to approach this? Well, first, we'd have to figure out the maximum number in the entire list. Let's call it max_val. Then, we could just generate every single possible subarray. For each one, we'd count how many times max_val appears inside it. If that count is k or more, we add 1 to our running total. The big problem here is, checking every single subarray takes a long time, especially if the input list is large. This feels like it might be order n squared, or even order n cubed complexity. We probably need a faster way. So let's rethink. The crucial part is that we only care about the maximum value of the entire original array. Let's find that value first. Once we have it, say it's max_val, the problem boils down to, how many subarrays contain max_val at least k times? This sounds like something we could potentially track as we scan through the array, maybe using a sliding window? Let's explore this sliding window idea. Imagine we have 2 pointers, left and right, both starting at the very beginning of the list. We'll also need the overall maximum value max_val. We move the right pointer one step at a time, expanding our window. We keep a count of how many times max_val has appeared within the current window defined by left and right. Now, the clever part, as soon as our count of max_val reaches k or more, we know that the current window left-right is good enough. But not just this window. Any subarray that ends at the current right position and starts anywhere from the beginning of the array up to the current left position must also contain at least k copies of max_val. How many such starting positions are there? Exactly, left positions, from index 0 up to left 1. So every time we have count greater than equals k, we add left to our total answer. Wait, we need to be careful. If we have too many max_vals, we should try to shrink the window from the left to find the smallest window ending at right that still satisfies the condition. Okay, let's refine. Move right. Update count if nums right equals max_val. Then, while count is greater than or equal to k, try shrinking from the left. If nums left is max_val, decrement count, always increment left inside this shrinking loop. After this shrinking loop finishes, meaning count is now less than k, the value of left tells us how many valid starting positions existed for subarrays ending at right. So we add left to our total answer after the shrinking loop. Let's reset that logic slightly to make it clearer. First, find the overall max value, max_val. Initialize our left pointer to 0. A count of max values in the window also to 0. And our final answer ends to 0. Now we loop with the right pointer from the start to the end of the array. Inside the loop, if the number at the right pointer is our max_val, we increment the count. Here's the core part. While our count is greater than or equal to k, it means our current window, left, right, might be too big, or just right. We try to shrink it from the left. If the element at left is max_val, we decrement our count because we're about to remove it from the window. Then, we always increment left. We keep doing this shrinking step as long as count is still k or more. After this shrinking process finishes, meaning the window left right now has less than k occurrences of max_val, the current value of left tells us something important. It tells us the number of valid starting positions, from index 0 up to left -1, that we could have used with the current right endpoint to form a valid subarray. Why? Because all those starting positions were outside the minimal window we just found. So at each step of the right pointer, after potentially shrinking the window, we add the current value of left to our total answer ANS. Finally, after the right pointer has gone through the whole array, we return ANS. Okay, here's the Python code that implements that sliding window logic. Don't worry if it looks a bit dense at first glance, we'll walk through the important parts next. It finds the max, initializes variables, loops with right, updates the count, shrinks with left when needed, and adds left to the answer. First up, we need to know what the maximum value in the entire nums list is. This code snippet does just that. It starts assuming the max value is -infinity, then loops through each number in the list. If it finds a number bigger than the current maximum it's seen so far, it updates the maximum. Pretty standard stuff. Or, you could just use the built-in max function if that's allowed. This is the heart of the solution, the sliding window itself. We initialize our answer ANS, the left pointer, and the max_count_in_window, all to 0. Then, we loop with the right pointer through the array. Inside the loop, first, we check if the number at the right pointer is our max_val. If it is, we increment max_count_in_window. Next comes the while loop. As long as max_count_in_window is k or more, we need to shrink the window from the left. Inside the while loop, we check if the number at the left pointer is max_val. If it is, we decrement the count because we're about to slide past it. Then, crucially, we always increment left. Finally, after the while loop, whether it ran or not, we add the current value of left to ANS. Remember, left now represents the number of starting positions from index 0 to left -1. That would form a valid subarray ending at the current right. So how efficient is this sliding window approach? It's pretty good. Finding the initial maximum takes time proportional to the number of elements. Let's call that order n, or big O of n. Then, in our main loop, the right pointer moves from the beginning to the end, so that's n steps. The left pointer also only moves forward, and can't go beyond n steps in total across the entire execution. Since each element is essentially looked at a constant number of times by either the left or right pointer, the overall time complexity is order n. That's much better than our initial n² or n³ idea. What about memory? We only used a handful of variables to keep track of the max value, the count, the pointers, and the answer. The amount of extra memory doesn't depend on how big the input list is. So, the space complexity is order 1 or constant space. Very efficient. Alright, let's quickly recap the main points. First, the problem simplifies significantly once you realize you only care about the single maximum value from the entire input array. The most efficient way to solve this is using a sliding window with a left and right pointer. Keep track of how many times the maximum element appears in the current window. When that count hits k or more, you know you have valid subarrays. The trick is to then shrink the window from the left side while the condition still holds. After shrinking, the value of the left pointer magically tells you how many valid subarrays end at the current right position. Add this left value to your total count. This whole process gives us a neat order n time solution using only constant extra space. Hopefully that breakdown made the problem and the sliding window solution much clearer. If this explanation helped you out, I'd really appreciate it if you hit the like button. Consider subscribing for more Leetcode explanations like this one. And if you have any questions or maybe a different way to solve it, feel free to drop a comment below. Finally, if you're feeling extra generous and want to support the channel, you can always buy me a boba using the link. Thanks for watching, keep practicing, and I'll see you in the next video. Happy coding!